and explainable development and evaluation of AI applications. Dita Tao Tatis. While AI enhances QFD, we can also reverse the perspective and use QFD to design AI systems themselves. This allows us to connect user needs, ethical principles, and AI functionalities right from the start. For example, values like transparency, fairness, privacy, and usability can be treated as explicit customer requirements in the first QFD matrix of an AI project. They are then systematically translated into technical specifications, ensuring they are not forgotten under time or cost pressure. The literature supports this. Feilman and Kranich highlight QFD's role in building trustworthy AI, while Villanueva proposes adaptive frameworks for AI governance. A real-world example comes from Mizuho Bank, which used QFD to design its AI-based chatbot. I will discuss this in more detail shortly. This approach also aligns with current AI standards such as ISO/IEC 22989 and ISO/IEC 42001, which stress user-centered and risk-based development, and, as negative cases like Amazon's biased recruiting algorithm show, failing to embed these requirements from the outset can have serious consequences. To keep AI development balanced across all critical dimensions, we can think of QFD as a compass. At the north point is ethical development, ensuring fairness, transparency, and compliance with regulations and societal expectations throughout the AI lifecycle. In the east, we place user-centric design, focusing on the systematic capture and prioritization of authentic user needs and expectations. The south point represents contextual adaptation, making sure that AI solutions are designed for their specific operational, cultural, and domain environments. And in the west, performance optimization drives continuous improvement in accuracy, efficiency, and robustness. Together, these four cardinal points form a navigational guide for aligning AI system specifications and evaluation criteria with a holistic perspective on value, trust, and technical excellence. AI systems that involve machine learning and user interaction face a particular challenge: aligning what users expect with how the algorithm actually behaves. QFD offers a way to make this connection explicit and traceable. A good example comes from Mizuho Bank in Japan. They used QFD to optimize their chatbot systems, starting with customer feedback to capture key needs such as emotional tone, fallback logic, and response speed. These were then prioritized within QFD matrices and mapped directly to the chatbot's functional and technical design. The result was a measurable improvement in customer satisfaction, showing that QFD can guide AI development not only towards technical accuracy, but also towards emotional resonance and overall usability. QFD provides a structured way to select and prioritize AI use cases by integrating user requirements early in the development process. In the house of quality, user needs, whether related to usability, reliability, or domain-specific functions, are mapped to technical solutions. This what-to-how linkage creates both traceability and transparency, which are essential in complex AI systems. Modern QFD goes beyond the traditional voice of the customer to include the voice of the business and the voice of the environment, as described in ISO 16355. This allows ethical principles, regulatory requirements, and societal values, such as fairness, transparency, and privacy, to be captured as quality requirements right from the start. These values can then be translated into measurable technical targets, making their implementation transparent and verifiable. This is particularly relevant for compliance with AI-related standards like ISO/IEC 22989, and it enables developers to document how ethics and user experience are embedded in the system for audits or certification. Finally, QFD integrates well with established development models like the V model, allowing requirements to be systematically verified and validated. This ensures that decisions can always be traced back to specific user needs, supporting both internal clarity and external trust. In many markets, sustainability has moved from being a nice-to-have to a decisive factor in customer choice. QFD can be adapted to integrate environmental metrics directly into the product planning process. Using life cycle assessment data such as CO2 footprint, recyclability, and energy consumption, we can position sustainability targets alongside traditional performance metrics in the house of quality. BMW Group applied this approach in the development of its electric vehicle platform. Here, sustainability targets were treated as core quality requirements and mapped to specific technical solutions within the same QFD framework used for performance and reliability. This integrated view ensures that environmental objectives are not an afterthought, but an equal driver of design decisions, helping companies align their products with both market expectations and long-term ecological goals. Let's now take a brief look at the future of QFD in the age of AI. Back in 2017, we introduced an agile variant of QFD designed for volatile environments, continuous QFD. The key idea was to keep adapting the product to customer requirements even between planned releases. This approach ensures that at any point in time, given the development constraints and deadlines, the product matches customer needs as closely as possible. In our current work, we build on this idea and extend it towards AI readiness. This means incorporating continuous data flows, AI-driven prioritization, and real-time feedback loops to keep both the QFD matrix and the resulting product specifications up to date. The figure illustrates how continuous QFD works as an ongoing cycle of feedback, prioritization, and implementation, ensuring that customer alignment is never frozen at a single point in time, but evolves dynamically. Machine learning projects often start without detailed design specifications. This makes it difficult to reproduce results or to apply systematic quality assurance. To close this gap, an adapted version of QFD was developed within the GSAME doctoral program at the University of Stuttgart by Villanueva Zacharias. This tailored approach aligns the full chain of requirements and solutions, starting from domain-specific needs, translating them into ML functionalities, breaking these down into components and software modules, and linking them to quality assurance metrics. The figure shows the overall structure of this QFD framework for ML, designed to make solution architectures both traceable and verifiable. By combining structured matrices with well-defined content templates, this approach ensures interpretability, traceability, and auditability of machine learning solutions. It enables teams to create complete, consistent specifications for each deployment, capturing not just technical details, but also requirements and quality targets. These specifications can then be stored in a central innovation knowledge repository. This makes them available for reuse, adaptation, and continuous improvement in future projects, reducing design effort and increasing consistency across an organization's ML initiatives. The figure illustrates how this multi-level deployment approach is adapted to the design of ML solutions. To take full advantage of AI and remain scalable in digital environments, QFD itself needs to evolve. QFD 5.0 envisions a modular, cloud-based, and fully collaborative approach. It incorporates APIs for integration, real-time dashboards for monitoring, and version control to manage changes over time. It also connects seamlessly with agile development platforms, enabling teams to update QFD matrices as part of their normal sprint workflows. The initiative behind QFD 5.0 aims to create an open toolkit, supporting adaptive matrices, automated voice of the customer mining, and alignment with ethical impact goals across industries. The figure outlines the conceptual model for this digital QFD infrastructure, showing how collaboration, automation, and openness can be embedded in the methodology's next generation, SAO. Organizations vary greatly in how mature their QFD practices are, especially when integrating AI. We propose a 5-stage maturity model. It begins with static matrices, progresses through AI-enhanced and predictive models, moves into adaptive systems, and ultimately reaches self-optimizing QFD environments. At each stage, organizations need more than just technology. They need new tools, training programs, and a culture ready to embrace continuous change. Given its rapid adoption of advanced manufacturing, AI, and collaborative innovation, Asia's industrial ecosystem is particularly well positioned to lead this transformation. I'm now coming to the end of my presentation. This review shows that QFD and AI complement each other in powerful ways. AI enhances QFD by enabling scalable and evidence-based voice of the customer analysis, predictive weighting of relationships, and real-time integration of feedback. Conversely, QFD provides AI development with a systematic framework for embedding user needs, ethical principles, and regulatory requirements directly into design decisions. The integration of the two offers clear advantages in speed, personalization, and customer alignment, while also guiding the ethical and functional design of AI systems themselves. Looking ahead to QFD 5.0, we will need a new generation of digital, collaborative tools that sustain alignment in real time. Future research should explore standardized QFD-AI interfaces, human-AI interaction design, and cross-cultural adaptation of QFD methods. In doing so, we continue the legacy of Professor Akao, evolving QFD into a methodology for systems that not only compute, but also interpret and serve. Many thanks for your attention.